Okay, balancing word equations, here we go. I'm not going to balance them, you can balance them. I'm going to show you the compounds. So number one, carbon plus oxygen yields carbon dioxide. So again, we have two reactants. Our reactants are carbon. Now carbon is in group 4, so it can exist by itself. Oxygen is diatomic, okay? It is very reactive alone, so therefore it's going to be found as a diatomic molecule with one double covalent bond. This yields CO2, okay? And obviously that's balanced because you see that thing at the end, that little number with the parentheses. I don't know why to do that. No coefficients. Okay, 2. Copper, the transition metal, can exist by itself, plus silver nitrate, Ag plus, NO3 negative, EOA, put them together. By the way, synthesis reaction, single replacement reaction. So now the copper is going to come in here, break this apart, and you're going to get, and this is what you're going to be predicting next packet. You're going to be getting silver by itself, because it's a transition metal, but you still have to work with copper and NO3. So you're going to go Cu, copper is 2 plus, copper 2 nitrate, NO3, 2, balance it out, the coefficients add up to 4. 3, again, single replacement. Zinc, transition metal, can exist by itself. Plus copper 2 sulfate, EOA. You guys should be doing it like that pretty much now. Again, single replacement. This is going to have enough energy to come in here and break this up. So what you're left with is this. The copper is going to be by itself over here. That's a U. And now you have to put these together. We know this is 2 plus, we know this is 2 negative. ZnSO4. Again, I don't expect you to know that yet. Next packet you're going to be predicting. So you will just cover up these products, you're going to figure them out. But we have a little more to learn first. 4, mercury 2 nitrate, Hg2 plus, NO3, 2 plus, what is it? Ammonium sulfide. Sulfide, okay, NH, oh, yep, okay. Yields. Okay, so what's going to happen is this. This is a double replacement reaction. So ultimately what's going to happen is you're going to have to switch partners. So mercury has an oxidation number 2. That's why we're going to get, this guy's going to break from this, and this guy's going to break from this. Okay? So now what would go together? Mercury and sulfur would go good together. So your mercury is plus 2. Sulfur is negative 2. So again, you're going to be given Hg. Mercury 2 sulfide will be HgS, the charges cancel, plus what are you left with? Polyatomic, the positive one first, ammonium nitrate, NH4NO3. So I'm giving you a little preview of predicting products here. Okay. 5, iron 3 hydroxide. Be careful of the parenthesis. Okay, you should know that already. We went through a lot of those. Oops, yields. What is it? Okay, iron 2 oxide. Okay, this is decomposition. These are going to be tricky to predict. So we'll learn those later on. So you're going to be getting iron 3 oxide. So if iron has oxidation number 3, oxide is 2 negative, it's going to be Fe2O3. And what else? What number are we on? Number 5, water. So those are your products right there. So right here, let's go back again. Synthesis, single replacement, double replacement, decomposition. Okay, I'm going to do one more, then I'm going to erase. 6, water decomposes. Easy. Gives you H plus O. Wait a minute, what's wrong with that? H doesn't want to exist by itself, it's diatomic. H2 plus O2. Because keep in mind, you've got, when you have one of these, it's not just one, you have 1 mole. So you have 10 to the 23rd of these. So when they split like that, you've got 10 to the 23rd plus whatever. You have hydrogens and oxygens. Who do we go with? Where do I go to? Well, not all of them will react. Some will go back to water, but you don't have to worry about that yet. So they want to make a chemical change. What would change them? Hydrogen, all the atoms of hydrogen will react with themselves, and so will oxygen. Okay? Again, I'm trying to give you a little taste of down the road. That's decomposition, by the way. Okay, 7. Okay, I don't know how much time I can do with these videos because I don't know how much we can, you know. Let's see, copper 2 nitrate, 7. Copper 2 nitrate, CuNO3, 2. What else we got? 7 plus water. Yields. Okay, so look here. So this is going to break and this is going to break. So you got some copper running around. You got some nitrate polyatomic ions running around. You got some hydrogens. You got some waters. I'm sorry, oxygens. So let's see. We got hydrogen nitrate. Another name for that is nitric acid. So that's taken care of, and this is taken care of. What's left over? There's still some excess hydrogen. You would also have copper 2 hydroxide. Copper 2 hydroxide. It would look like that. Let me see if you can see that. Y'all see that? Okay, that's a 2 right there. Double replacement reaction. Number 8. Phosphorus plus oxygen. Okay, P can be by itself. It doesn't need to be diatomic. Plus O2. Diphosphorus pentoxide synthesis, P2O5. 9. Iron plus hydrochloric acid. Iron plus HCl. Okay, single replacement. So now look what's going to happen here. We're going to have, this is going to come in here and break. So you're left with iron atoms, you're left with hydrogen and chlorine atoms. So iron's here. So we can make an ionic compound, a metal nonmetal. So we're going to get iron. And this was, we're going to assume iron 2 chloride, so we're going to go FeCl2. Oh, we don't need the parenthesis there. Sorry. FeCl2. Plus, be careful, you have a lot of these atoms. Do you think they're going to want to be unstable? No, so they react with themselves. H2, single replacement. 10. So this is double replacement, but acid-base neutralization, which we'll learn. Sodium hydroxide plus phosphoric acid. Is that what I'm on? Yep. Okay. Phosphoric. So you have to use the phosphate ion, H plus 3PO4. Phosphate ion because it's a Nick ending. Yields. This is double replacement, also acid-base neutralization. This breaks apart. This breaks apart. So right here you have a strong base. This is an acid. You put them together, you make something, you make a salt. Well, what's our salt? Metal, non-metal. Here's our metal. Here's our non-metal polyatomic ion. You're going to make sodium phosphate plus, what do you have left? Hydrogen atoms and OH, H2O. So this is double replacement, but also it's acid-base neutralization. You get a salt and you get water every time. 11. Antimony, Sb, plus chlorine. Now wait a minute, it's diatomic, it's a halogen. Antimony trichloride. Okay, sodium chlorate. Let's do one more down here. Sodium chlorate, Na. You guys got to know these. ClO. What do we got? Decomposition, that's synthesis. Decomposition. So you have decomposition of a chlorate. You get salt plus what? So you have NAs running around all crazy, Cl's and O's. Who's going to go with who? You're going to get a metal, non-metal salt, and then you're going to get oxygen by itself. Why would it do that? So they're going to react with themselves, O2. Because remember, you got 10 to the 23rd, or whatever. When you balance, you have a lot there to work with. Okay? Some of this will go back as that. Not all of it reacts, and we'll get to that next packet. Okay. I'm going to do a few more. I think you get the gist of these. Let's see. Let's go with 16. Barium chloride. Barium has a positive 2 charge. Barium chloride plus magnesium sulfate. Mg2 plus SO42 negative. Yields. Let's see, what do we got? So, okay, I can do it. So we're going to break this apart. Break, break. So we have moles or mole, whatever you balance, of atoms. So I got barium atoms running around. I got chlorine atoms running around. I've got sulfate polyatomic ions running around. I got magnesium. So assume we make something new, who's going to go with who? Would chloride go with sulfate? No, they're both negatively charged. So I already had barium chloride, so now I have a new combination, new ionic compound, magnesium chloride, MgCl2. So that's taken care of. What's left over? Barium sulfate. See how easy that is when you predict products? Again, you'll get good at that as time goes on, but you can't do it unless you know your nomenclature. Let's go to 24. Silver sulfate, Ag plus 1, SO42 minus, plus acetic acid. Oh, that's a nasty one. I don't want to do that one. No. Aluminum chloride, excuse me. Yeah, acetic acid, don't worry about. Aluminum chloride, here we go. AlCl3. Double replacement. This is double replacement. Double replacement. This is going to break apart. This is going to break apart. So I don't know how many moles you got depending on how you balanced it. So you got some silver running around here. Sulfates running around here. You've got aluminum running around here, and you got chlorine running around here. We have to go through a chemical change. So aluminum chlorine to right over here. Some will go back as such, but something new will be made. Can we have silver aluminide? No. Can we have silver chloride? Yes. Ag plus 1, Cl negative. Can I have aluminum sulfate? Absolutely. Al, SO4, 2 there, 3, right there. So again, all we do is break it apart, form a new combination. But you have to know who would go with who. Go to, let's see, go to 18. Switch up. What's 18? Ammonium carbonate. NH42CO3, because that's a plus 1. Decomposes into ammonia, NH3. Plus, okay, so look up here. So you've got ammonia that's already decomposed, and now here's the thing. You've got some extra hydrogen. You have a lot of hydrogen atoms. Only nitrogen takes each 3, so you still have some room to make something else. Carbonic acid, and you notice this is carbonate. This has an ATE ending. It turns into the IC ending to make H2CO3, and then you balance it out. I think that's pretty good. I think we did a lot. The video is going to take forever to download. So again, you don't need to know how to predict, but I'm just giving you a little piece of advice. Bonds break. They stay together. You have to figure out who should they go with, and many times it's a metal, non-metal. If you understand your nomenclature, you can do anything. But all you got to do right now is worry about the nomenclature at this point, okay? Okay, so that's that. Make sure you watch it, and then tomorrow you should so improve. But real quick, I do want to show you this. Don't forget these. We call them Brinkelhoff elements. We've mentioned in class like once. Write this out big on your paper. And put a parenthesis around it too. Why? These are all the diatomic elements. They're all individually very reactive. Bromine's reactive. Iodine's reactive. Nitrogen's reactive. Chlorine's reactive. Hydrogen's reactive. Oxygen's reactive. Fluorine is reactive. That's why they're found as Br2. See how they distribute? I2, N2, Cl2, H2O2, F2. So we call them diatomic. We call them the Brinkelhoff elements. So if you see any of these, they are very reactive. Now keep in mind, you know, some people want to know, well, why isn't phosphorus? You know, because phosphorus is similar to nitrogen in the fact that it's got 5 valence electrons. But phosphorus has a larger radius. It's not as reactive as nitrogen, which has a smaller radius. Okay? So that's why this can't exist by itself, or rarely ever. This can more often. So that's why these guys are the diatomic elements. Don't forget Brinkelhoff, and then put in parentheses 2. Okay? Get it done. That's it. Hopefully this helped. I've never taught this way before, but hopefully it'll work.